Alright, and down here towards the end is the shortest wavelength. The energy emitted from these waves, these different types of waves, goes the opposite direction. So the energy arrow goes from top to bottom here. So these have the highest energy, and the longer the wavelength has the least energy. Okay. So let's just start with, and here if you couldn't have seen that, I'm sorry. So let's just start labeling them in order from least amount of energy or the longest wavelength to the greatest amount of energy or the shortest wavelength. First thing we have is the radio wave, then microwave, then we have infrared waves or rays, either way they're interchangeable, visible light, ultraviolet rays or waves, which are also known as UV. Then we have X-rays, and last but not least, gamma rays. Okay, so as we said, the longer the wavelength, the least amount of energy. Let me just show you what we mean by wavelength here. So if you look at a wave, and let's just take the infrared wave here because it's easy to see, you're going to go from top of the wave to the next top. So that would be the length, the wavelength. And as you can see, this one, if you went ahead and peeked it out, wouldn't peak till over here, so obviously this is way longer than this. And then if you get down here, you can see that these are much shorter. So that's what we're meaning by the wavelength, okay? So the longer the wavelength, the least amount of energy. So what do we use radio waves for? Well, we use radio waves for TV signals and radio signals. Trying to think, think about it. Microwaves, you're all familiar with the microwave we have in our kitchen to heat our food. That would be in the kitchen they use. But also microwaves, if you didn't know, are used in cell phones. And they are used in radar detection. Radar detection, like from police officers maybe trying to catch a car that's going too fast. That would use a radar detector. Infrared waves. Well, infrared waves, visible light, and UV are some of the forms of energy that you are familiar with, even though you didn't know it belonged to the electromagnetic spectrum. But infrared waves are the heat you feel when you go outside and the sun's shining. That's the heat you feel. Okay? Infrared waves, though, are also used for things like finding nebulas, birthplaces of stars, and stars themselves. So they're used in space technology. Some of you might be familiar with the infrared lamps, the heating lamps that can warm your skin. Some of you might be familiar with the infrared lights to hunt with. So there's different things that we use infrared for. Visible light. Well, visible light is the light you see, right? So this is the light you see. And visible light is actually what we refer to as white light, but it is not white. So when we're looking outside, it looks white to us, but visible light is actually made up of many colors. Actually, the colors of the rainbow. And we're going to look at what they are. It's made of all the colors of the rainbow. One way to remember the visible light is an acronym we use to remember the colors, and it's ROY, R-O-Y, G, B-I-V, BIV. Roy G. Biv helps us remember the colors of the rainbow. So we start off with red, and then orange. Remember, the colors of the rainbow is what light is made of. When light rays from the sun get bent or refracted, they show the colors that that white light is actually made of. And this is Roy G. Biv, red, orange, yellow, green, blue, indigo. I have a blue here. Blue. Indigo is a cross between blue and purple, so I'm just going to make my blue a little bit bigger and go over it with a little purple. And violet or purple. So those are what visible light is actually made of, all of these colors. So when you're looking at white light, remember that. It's not white. It's made of Roy G. Biv. Alright, so the next thing, ultraviolet rays. You know all about, some people call them UV. I'm sure you've heard of them, and you've also experienced them. If you've ever had a sunburn, or even if you get tanned, that is the result of not heat and not light, but the ultraviolet rays that are coming along with the light and heat. Okay, so UV rays cause sunburn or tan. UV rays are also valuable in the production of vitamin D. So when you take in vitamin D in your milk or in your dairy products, you also need exposure to UV light to actually turn that provitamin D you've eaten into actual vitamin D in your body. So you have to have some exposure to UV light or UV rays. You can actually just walk outside and it's enough to get enough exposure to convert that provitamin D that you ate into vitamin D in your body. Alright, the next one we're going to talk about is X-rays, and you all know pretty much about X-rays. X-rays are used in medicine and dental areas. X-rays are dangerous, so is UV. UV, X-rays, and gamma rays is where the electromagnetic spectrum is dangerous, becomes dangerous to life. So let's just kind of draw us a little line here, showing that this is where these rays can become harmful. I'll write it over here. So these rays from UV on down are harmful to life. So we do protect ourselves from them. Think about it. We protect ourselves from ultraviolet rays when we go to the beach or somewhere like that. We protect ourselves by using sunscreen, for example, as a protection. Alright, and as far as X-rays go, we get X-rays in medical and dental areas, but when we go into the X-ray arena, we also get areas that were not X-raying covered with a heavy lead cloak. This is to protect the rest of your body from the X-ray waves that are dangerous. Also, when you get them done with your teeth, they put that little cape on you as well to cover areas that should not be exposed to those harmful radiance. The X-ray technician also steps out of the room, and that's why, because excessive exposure to X-rays is deadly. Alright, let's move on to gamma rays. Gamma rays are very, very, very short wavelength, but they have the highest amount of energy, and they are the most dangerous to life. These are, however, used in an area of nuclear medicine. So if you've ever heard of a cancer patient getting radiation therapy, this is what they're getting. It can be used to accurately pinpoint an area of cancer, and that small area gets radiated and with gamma rays until hopefully it shrinks that tumor. Alright, so these are the types of waves, these are the uses or the effect. Like we said, at one point, right here starting at ultraviolet light, they get harmful to life. So we don't want to expose ourselves to any more than we have to of these. So what is the relationship between wavelength and energy? Well, the longer the wavelength, the least amount of energy. The shorter the wavelength, the higher amount of energy. The higher the energy, the more harmful to life. Okay? So let's note that down here. We want to note the shorter the wavelength, the higher the energy, meaning the more dangerous to life. Or more harmful to living things. So let's look up here real quick. So what actually gives us provides life some protection from these rays that are coming from our sun or any star, ultraviolet, X-ray, and gamma? How is it that we're not all dead if exposure to them is dangerous? Well, we do have something in our atmosphere that protects us from some of these harmful rays. What is that? If you said ozone layer, you're absolutely right. So the ozone layer adds protection from these harmful rays. So ozone protects from most of them. Okay? So we do get some protection. Once again, let's look at our energy. So energy is from the longest wavelength to the shortest is increasing. So it's increasing in this direction. Whereas the wavelength is longest here with the least amount of energy and shortest down here with the most amount of energy. So just so you understand that relationship. Also, if you look at what's known as frequency, you all know that frequency just means how often something happens. So if we look at the frequency of wavelength or frequency of waves, I don't know if I spelled that right, but okay. So if we looked at this, and this is, let's say this is a second in time, how many waves passed us by? Well, you just have to count the peaks. So we have 1, 2, 3, 4. So we had 4 waves per second. But if you go up here, we only have 1, 2, 3 per second. Whereas up here, we don't even have 1 per second. We have about 1 per second. So you can see there's a difference in how many waves per second. And obviously, the shorter the wave, the more you're going to get in a second. So the frequency of wave also corresponds to the wavelength. So the shorter the waves, the more frequent and higher energy. And that was the workshop on electromagnetic spectrum of energy.